Our topic for the paper presentation is Design Considerations for a 5G Network Architecture. The authors for this paper are Patrick Corvo-Agyapong, Mikio Iwamura, Dirk Steil, Wolfgang Kais, and Enes Penchapor. This will be the agenda for the presentation. We will begin with introduction, following which we will take a look at current trends in mobile networks. Further, we will discuss the challenges, enablers, and design principles, followed by architecture vision for 5G mobile networks. Then we will take a look at the issues in the proposed network architecture. Finally, we will conclude with proof of concept. On an abstract level, 5G will be a two-layer network architecture consisting of radio network and a network cloud, which will be integrating enablers such as small cells like picocells and femtocells, massive MIMO, control and user plane split. We will also discuss network function virtualization and software-defined networking in detail. So what are the current trends in technology? As we all know, mobile data consumption is exploding due to increase in number of devices and desire for anywhere, anytime connectivity. Battery life of devices is also becoming an important issue for many end users. Furthermore, the Internet of Things is becoming a reality. Now, with currently existing 4G, we cannot accommodate the advances in technology. For example, concepts like augmented reality, real-time gaming, autonomous cars need an end-to-end latency of 1 millisecond, whereas with 4G, minimum latency possible is 50 milliseconds. Clearly, we need a new generation of mobile networks. So based on the discussed trends and many more, following challenges need to be addressed by 5G. We will be needing higher system capacity, higher data rate, lower end-to-end latency, massive device connectivity, cost reduction for a sustainable system, and consistent quality of experience from end-user perspective.
Yes. Mobile networks will have to support 1000 times increase in traffic and 100 times increase in data rates. Because of evolution in technology, today we have n number of connected devices which needs round the clock data services. These increase in system capacity cannot be handled in 4G LTE networks. So this increase in capacity has to be addressed in radio access networks as well as in backhaul and fronthaul. Before going into further description, we will discuss what is fronthaul and backhaul and how they address the growing challenges in helping today's massive mobile traffic loads. These links which interconnects macro cell site which is referred as baseband unit to mobile telephone switching office based on Ethernet over fiber links via 1 gigabytes per second physical interface to the macro cell site. Whereas fronthaul is associated with a new and different type of radio access network architecture consisting of centralized baseband controllers and standalone radio heads installed at remote cell site locates tens of kilometers away. The optical link that interconnects these centralized baseband units and remote radio heads is fronthaul. Now we go back to the system capacity and data rates. System capacity and data rates is subcategorized into 4 parts which we will discuss as we proceed. Now we will discuss about spectrum. Opportunity for more spectra include higher frequency bands, that is millimeter waves, and massive MIMO techniques. Let us see how MIMO works. MIMO is abbreviated for multiple input, multiple output. Massive MIMO are operated fully, coherently and adaptively. Extra antennas help by focusing the transmission and reception of signal energy into ever smaller regions of space. This brings huge improvement in throughput and efficiency. Massive MIMO can be exploited to extend the coverage of high frequency bands by relying on beamforming gains. Now let us see a simulation of beamforming in antennas and the modulation and coding schemes for spectral efficiency. As the user equipment moves, we can see how beamforming is carried out. Higher order modulation and coding schemes such as 256 quadrature amplitude modulation increase spectral efficiency and can be combined with massive MIMO to increase system capacity. With such techniques in place, new schemes such as non-orthogonal multiplexes, filter bank multicarrier, and sparse codon multiplexes can further be utilized to increase spectral efficiency.
We just spoke about spectrum efficiency while the simulation was running. Now let's speak about network densification. Network densification refers to the dense deployment of many small cells. The attenuation that high frequencies suffer is no longer seen as a drawback but a blessing in disguise, making them suitable for use in smaller cells. To allow efficient improvement of capacity at critical locations, it is desirable that coverage and capacity be addressed independently. This can be realized through an architecture where control and user data planes are split among different cells. The benefit of this approach is that user plane resources can be scaled independently of control plane resources. This allows more user plane capacity to be provided in critical areas where it is needed without the need of providing co-located control plane functionalities. Thus, more flexible deployments at lower cost can be realized. In such a control and user plane split architecture, macro cells can provide coverage and small cells can provide localized capacity. Techniques like massive MIMO and higher order modulation and coding schemes can be employed in small cells to boost throughput. Additionally, local offload through techniques such as network controlled device to device communications can further increase achievable system throughput. End-to-end latency, which is the round-trip delay between your transmitter and receiver, is an important factor for real-time applications. Safety-critical applications for cars and humans built around vehicle-to-vehicle and vehicle-to-infrastructure communication require very quick request response and feedback control cycles with high availability and reliability. In order to realize these applications, networks must be able to support a target of 1 millisecond end-to-end latency with high reliability. Innovations in air interface, hardware, protocol stack, backbone and backhaul, as well as network architecture can help us meet this challenge. A new air interface with new numerology such as shorter transition time interval can reduce over-the-air latency to a few hundred microseconds. Efficient design of non-access stratum could also help reduce end-to-end latency. There are a lot of examples with regards to technology, but we have listed the emerging applications such as remote controlled robot, automated driving, augmented reality and virtual reality. Next challenge is massive number of connections. Due to huge diversity in the type of devices, challenges to support the service requirements in an efficient manner. Techniques like intelligent clustering and relaying can be used to support hyperconnectivity. For instance, one device can act as a gateway to aggregate traffic, thereby reducing signaling load on the network. Next challenge is cost. Traditionally, the base station implements the functionality of user plane and control plane, which requires additional hardware for making the routing of control and data packets possible. NFV and SDN allows us to implement this functionality in software running on used data centers and cloud. This way, the base stations can become simpler in hardware by implementing only layer 1 or 2 in the protocol stack and moving higher level functionality into network cloud. Let us see a video for better understanding. A typical mobile infrastructure is composed of access point and core network. Currently, this core network is built with specialized hardware elements. In 5G, these elements will be virtualized and implemented in network cloud. The operation and business support application will also be transferred to the cloud. This will be possible using network function virtualization. NFV will use general purpose hardware to provide networking, computing and storage. SDN will also be used along with NFV to increase network end-to-end transport efficiency. Intelligent energy management techniques provide a viable means to reduce overall network operations cost. Energy efficient hardware design, low power backhaul, and intelligent energy management techniques, especially in ultra-dense networks to put base stations to sleep when not in use can all contribute to reduce the cost of operating of a 5G network. Moreover, pooled hardware resources can be shared among multiple functions, thus realizing multiplexing gains and lowering the amount of necessary hardware. Next, we will discuss quality of experience. Quality of experience describes the subjective perception of a user as to how well the application works. Despite the diversity of QoE requirements, providing low latency and high bandwidth generally improves QoE. Delivering an app with too low QoE leads to user dissatisfaction. Let us summarize the key elements in the 5G architecture. The architecture comprises of two logical network layers, a radio network and a network cloud. The radio network comprises of only minimum set of layer 1 or 2 functionalities. Separate provisioning for coverage and capacity in the radio network is achieved by control or user plane split architecture and different frequency bands for coverage and capacity. A lean protocol stack achieved by consolidating redundant access stratum and non-access stratum functionalities is proposed. Such integration allows simplification of mobility management, session management, and security procedures. Devices with limited resources such as low-powered devices connect non-transparently to network through one or more devices that have more resources. Network paging procedures can be used to initiate connections to such devices, reducing signaling traffic and power consumption. Nesting and relaying is used to support this. Dual connectivity of terminals to multiple base stations can exploit aggregate use of spectrum deployment at different base stations. Local offloading can be achieved through network controlled device-to-device communication. Data-driven network intelligence. The architecture allows network cloud to collect various types of user-centric, network-centric, and context-centric data. By providing APIs to the network cloud, the collected data can be used in various forms for public and commercial purposes. For example, the APIs can be used to facilitate new businesses based on selling knowledge about network conditions as a service to over-the-top players, which can allow them to provide consistent service quality to end users. Further, we will discuss some more points about network cloud. The physical realization of network cloud could be tailored to meet various performance targets. For example, instances of user plane entities and control plane entities could be located close to the base stations to meet needs of latency critical services. To support latency critical services, for example, it may be better to connect radio unit 3 to a small nearby data center rather than a large data center farther away. On the other hand, remote radio unit 1 can be connected to a large data center located farther away rather than a nearby small data center if support for latency critical services is not required. By employing SDN and NFV, control plane entities and user plane entity functions in the network cloud can be deployed quickly. For instance, when a local data center is unable to cope with a flash crowd, additional capacity can be borrowed quickly from other data centers. The network cloud uses intelligent algorithms to provide real-time insights for efficient resource management, mobility management, and local offload decisions. Several issues need to be addressed in order to realize the proposed network architecture. One important issue that must be addressed is how older networks will interface with the new network architecture. An intermediate step wherein the migration of older core and radio access networks to cloud could be envisioned. Centralization of resources could lead to performance bottlenecks, higher latency, and single points of failure. Additional robust measures will be required to avoid devastating impact on service availability if the central entity fails. Backhaul will also be an important issue, especially for user deployment. Local breakout may be required for efficient routing in this case. New paradigms of identity management and charging need to be developed to cope up with the huge variety and number of devices expected to be connected to the network. An initial proof of concept with real-time simulator evaluation is presented by the authors to demonstrate the potential of the proposal for downlink transmission. LTE-based microcells using 20 MHz bandwidth at 2 GHz and small cells at higher frequency bands together with MIMO are demonstrated. Each macrocell using 2 transmit antenna with antenna gain of 14 dBi and total transmit power of 49 dBm were used. The image shows the deployment environment in Tokyo with 7-cell model of inner state distance of 500 meters. Ray tracing was applied using vertical plane launch method to emulate a real propagation environment. Now we will see the performance of the network based on the proof of concept. We can clearly see the improvements in spectrum usage for macro cells and small cells. The power spectrum density becomes lower as the spectrum bandwidth is extended to 1 GHz. By simulating each of the candidate 4G technologies, we see 1300 times system throughput gains as a combination of dense deployment of small cells employing massive MIMO. 90% of the users are able to achieve data rates in excess of 1 gigabits per second with such a network. Thus, after discussing the design challenges and architecture using 5G networks, we have good understanding of network architecture and advancements. With this, we conclude the presentation. For further reading, we have included references. Thank you.